A wildfire burning in the North Cascades is sending a huge plume of smoke into the air.
In this special two-part mini-series of Solomon's Outdoor Adventures, we're going to go on a field trip throughout the Pacific Northwest.
The Cascade Range is literally shaking and rumbling for the past months and years, no thanks to its hazardous active volcanoes. We're talking about dangerous seismic activities, potential massive glacier movements, and other catastrophic natural disasters that can destroy nearby local communities and infrastructures. These volcanoes have breathtaking beauty, but it comes with a price: unpredicted, terrifying earthquakes. Move aside because you might not want to hike near the range for your next holiday trip. A chain of iconic peaks. Cascade Range is considered dangerous, and the threats it poses to surrounding communities and the broader region. The Cascade Range is part of the Pacific Ring of Fire, a region of high volcanic and seismic activity caused by the movement of tectonic plates. The range's volcanoes exist due to the Cascadia subduction zone, where the Juan de Fuca plate is forced beneath the North American plate. This subduction creates magma that rises to the surface, forming volcanoes. The volcanic activity in the Cascade Range can trigger several hazardous events, including pyroclastic flows, ashfall, lava flows, and lahars, which can devastate communities and ecosystems for miles. Beneath the Cascade Range lies the Cascadia subduction zone, a 1,000-kilometer fault where the Juan de Fuca plate is being subducted under the North American plate. This fault has the potential to generate massive megathrust earthquakes, similar to the ones seen in Japan in 2011 and Chile in 1960. A rupture of the Cascadia subduction zone could result in a magnitude 8.0 to 9.0 earthquake, causing widespread devastation across the Pacific Northwest. Violent shaking could destroy buildings, roads, and bridges across cities like Seattle, Portland, and Vancouver. Coastal communities in Washington, Oregon, and Northern California would face deadly tsunamis triggered by the earthquake. Landslides, ground liquefaction, and aftershocks could worsen the destruction. The potential for a massive Cascadia earthquake adds a layer of danger to an already volatile geological region. Volcanic eruptions in the Cascade Range have the potential to produce massive ash clouds, which can spread hundreds of miles downwind. Ashfall poses numerous hazards. Volcanic ash can cause respiratory issues, especially for people with existing health conditions. Ash can damage airplane engines, halt flights, and make roads impassable. Ashfall can pollute rivers, lakes, and reservoirs, affecting drinking water supplies. Ash can destroy crops, disrupt power supplies, and damage buildings, leading to significant economic losses. The eruption of Mount St Helens in 1980 demonstrated the far-reaching effects of volcanic ash, as ashfall was recorded as far away as the Midwest. The Cascade volcanoes host some of the largest glaciers in the contiguous United States. While these glaciers contribute to the region's natural beauty and water resources, they also pose significant dangers. Rising volcanic heat or climate change can cause rapid glacier melt, triggering lahars, flooding, and landslides. The combination of steep slopes and unstable glaciers can result in catastrophic avalanches or debris flows. Mount Baker and Mount Rainier in particular are known for their large active glaciers, which make them more susceptible to these hazards. The danger of the Cascade Range is amplified by the proximity of its volcanoes to densely populated cities and towns. Urban centers like Seattle, Portland, and Vancouver lie within the influence of these volcanic and seismic hazards. Millions of people are at risk from earthquakes, lahars, ashfall, and other volcanic activity. Additionally, many communities live in the path of river valleys, where lahars from volcanic eruptions or glacier melt could travel quickly, giving little time for evacuation. The Cascade Range's combination of beauty and danger demands constant vigilance and preparedness from residents, emergency responders, and scientists. Let's get to know the most dangerous volcano in the range: Mount Rainier. The Cascade Range, stretching from British Columbia to Northern California, is home to some of the most prominent and active volcanoes in the world, including Mount St Helens, Mount Hood, and Mount Adams. However, among these volcanic giants, Mount Rainier stands out as the most dangerous volcano in the Cascade Range. While it has not erupted in over 1,000 years, its unique combination of massive glaciers, steep slopes, proximity to densely populated areas, and potential for catastrophic lahars makes it a significant threat. Mount Rainier, the tallest peak in the Cascade Range at 14,410 feet, looms as both a natural wonder and a geological hazard in the Pacific Northwest. Known for its massive glaciers, iconic presence, and active volcanic history, Mount Rainier has recently experienced an increase in seismic movements, sparking interest and concern among scientists and nearby communities. Though subtle, these movements highlight the volcano's dynamic nature and its potential to pose risks. Mount Rainier's seismic movements consist of earthquake swarms, clusters of small tremors occurring over days or weeks. These earthquakes are generally low in magnitude, ranging from 1 to 3, and occur deep beneath the volcano, often between 2 to 6 kilometers below the surface. While not immediately threatening, these events provide important clues about the volcano's behavior and subsurface processes. Rising or shifting magma can fracture surrounding rock, causing small earthquakes. Heat from magma interacts with the extensive glacier-fed water systems beneath Mount Rainier, producing steam and pressure that can trigger tremors. Mount Rainier lies within the influence of the Cascadia subduction zone, where the Juan de Fuca plate collides with the North American plate, building stress that can lead to earthquakes. While seismic activity is common for active volcanoes like Mount Rainier, an increase in frequency or intensity signals changes within the volcanic system that warrant close attention. In recent months, scientists have detected a noticeable increase in low-magnitude earthquakes beneath Mount Rainier. This activity, while not extreme, is significant for several reasons. The clustering of small earthquakes suggests changes in pressure or movement of fluids beneath the volcano. The tremors are occurring deep within the volcanic structure, likely related to the movement of magma or the interaction of hydrothermal systems. Mount Rainier has experienced similar seismic swarms in the past without erupting, but monitoring these patterns helps scientists assess the volcano's current state. While Mount Rainier's recent activity does not indicate an imminent eruption, it highlights the volcano's potential to become active. A future eruption could produce lahars, destructive volcanic mudflows triggered by melting glaciers. These lahars could devastate river valleys and towns downstream, such as Orting, Puyallup, and Tacoma. The region's proximity to the Cascadia subduction zone means that Mount Rainier's seismic activity may also reflect regional stress buildup, which could lead to larger earthquakes affecting the entire Pacific Northwest. Increased heat and pressure beneath the surface could destabilize glaciers, leading to avalanches, floods, or other hazards. Mount Rainier has the largest glacial system of any volcano in the contiguous United States, with over 25 major glaciers covering its slopes. During an eruption, heat from rising magma could rapidly melt the glaciers, generating lahars that flow down river valleys at speeds exceeding 40 miles per hour. Lahars can travel for tens of miles, sweeping away everything in their path, including buildings, bridges, and roads. Historical evidence shows that lahars have occurred even without eruptions due to landslides or small volcanic events. The Osceola mudflow, which occurred about 5,600 years ago, traveled over 50 miles, burying large areas of what is now the Puget Sound lowlands. Seismometers detect the location, frequency, and magnitude of earthquakes, helping scientists track magma movement and tectonic stress. GPS and satellite imagery are used to detect subtle changes in the volcano's shape, which could indicate magma rising beneath the surface. Instruments measure volcanic gases such as sulfur dioxide, carbon dioxide, and water vapor. An increase in gas emissions often signals rising magma or changes in hydrothermal systems. Heat sensors monitor temperature changes around Mount Rainier, particularly near vents and glacier-covered regions. Given Mount Rainier's location near densely populated areas, the recent seismic movements underscore the need for public awareness and preparedness. Local governments, emergency management agencies, and scientists have emphasized several steps. Efforts to improve early warning systems ensure communities receive timely alerts about volcanic or seismic activity. Communities downstream from Mount Rainier have developed evacuation routes and drills to respond quickly to lahar warnings. Outreach programs, educate residents about volcanic hazards, preparedness strategies, and how to respond during an emergency. Preparedness is key to reducing the risks associated with volcanic unrest, particularly for vulnerable communities living in the paths of potential lahars and floods. The recent seismic movements at Mount Rainier are a reminder of the volcano's dynamic nature and its potential to pose serious hazards to nearby communities. While the earthquakes are currently small and pose no immediate danger, they highlight the importance of continuous monitoring, scientific research, and community preparedness. Mount Rainier, often celebrated for its beauty, must also be respected as an active geological force capable of significant change. By staying vigilant and fostering collaboration between scientists, emergency planners, and the public, we can better prepare for any future activity, ensuring the safety of the region and its residents. Mount St Helens. Mount St Helens, located in the Cascade Range of Washington State, is one of the most well-known volcanoes in the United States due to its explosive 1980 eruption. Since then, this active stratovolcano has remained a focal point for scientists and the public alike. Recent surges in earthquake activity around Mount St Helens have reignited concerns about its potential for future eruptions. These seismic events provide critical clues about the volcano's activity, its behavior beneath the surface, and the importance of preparedness in a geologically active region. The earthquakes at Mount St Helens are primarily caused by magma movement deep below the volcano. As magma rises toward the surface, it creates pressure and fractures the surrounding rock, leading to seismic activity. These earthquake swarms, clusters of small repetitive tremors, are often signals that magma is shifting or accumulating in underground chambers. While small earthquakes, often less than magnitude 3, are common around Mount St Helens, a sudden increase or surge in earthquake frequency and intensity can indicate changes in the volcano's magma system. Such seismic activity serves as a warning that the volcano is experiencing unrest and may be reawakening. But what did we learn from the 1980 eruption? The catastrophic eruption of Mount St Helens on May 18, 1980, remains one of the most significant volcanic events in US history. It was preceded by a dramatic increase in earthquake activity. Beginning in March 1980, hundreds of small earthquakes were detected each day, signaling magma movement beneath the volcano. These tremors culminated in a massive eruption that triggered a lateral blast, landslides, ashfall, and pyroclastic flows, causing widespread destruction and loss of life. The 1980 eruption taught scientists that earthquake swarms are often early warning signs of volcanic activity. This event reshaped how monitoring systems are used to track seismic and volcanic changes, particularly in the Cascade Range. In recent years, Mount St Helens has experienced periodic earthquake surges, sparking public concern and scientific interest. These surges are closely monitored by the US Geological Survey and the Pacific Northwest Seismic Network, or PNSN, which have deployed an extensive network of seismometers, GPS sensors, and gas detectors around the volcano. Swarms of small earthquakes typically occur 10 kilometers below the surface, suggesting magma movement or adjustments in the volcanic system. Minor ground swelling or deformation is often observed alongside seismic activity as magma pushes upward. Changes in volcanic gas emissions, particularly sulfur dioxide, may indicate that magma is approaching the surface. These tools help scientists determine whether the earthquake surge is a result of magma movement or other factors, such as tectonic stress or hydrothermal activity. Still, anything can change, and unexpected volcanic activities can still occur at any given time. After the 1980 eruption, Mount St Helens has experienced cycles of magma replenishment, where new magma enters underground chambers. This process causes pressure to build and triggers seismic swarms. Mount St Helens lies in a tectonically active region where the Juan de Fuca plate subducts beneath the North American plate. This ongoing collision can generate earthquakes that interact with the volcano. Heat and pressure from magma can cause underground water systems to boil and expand, creating additional stress and small seismic tremors. While these surges do not necessarily mean an eruption is imminent, they serve as reminders that Mount St Helens is still active and capable of significant volcanic events. If seismic activity continues to increase, it may precede a new eruption. Hazards include ashfall, pyroclastic flows, lahars or volcanic mud flows, and landslides, which can impact nearby communities, water systems, and infrastructure. An eruption could disrupt air travel, agriculture, and transportation across the Pacific Northwest. Ash clouds can spread hundreds of miles, affecting cities and ecosystems far from the volcano. The earthquake surge underscores the importance of public awareness and emergency preparedness. Communities near Mount St Helens must be ready for potential evacuation and have plans in place to minimize the risks. Since the 1980 eruption, advancements in technology and monitoring have significantly improved scientists' ability to track volcanic activity. Modern seismometers can detect even the smallest earthquakes, helping scientists identify patterns in seismic activity. Tools like INSAR, interferometric synthetic aperture radar, monitor ground deformation, providing real-time data on magma movement. Improved models and data-sharing platforms allow authorities to issue timely warnings and reduce risks to communities. Mount St Helens remains one of the most closely monitored volcanoes in the world, ensuring that any significant changes are quickly detected and communicated to the public. The recent earthquake surges at Mount St Helens serve as a reminder that the volcano is still alive and capable of powerful eruptions. While these seismic events may not immediately lead to volcanic activity, they highlight the importance of continuous monitoring, preparedness, and public awareness. The lessons of the 1980 eruption emphasize the need to respect the power of nature and use science to stay ahead of potential hazards. By combining modern technology with historical knowledge, scientists and communities can work together to understand and mitigate the risks posed by Mount St Helens, ensuring that the region remains resilient in the face of its volcanic future. Mount Baker. Mount Baker, a snow-capped stratovolcano in the Cascade Range of Washington state, is both a symbol of natural beauty and a potential geological hazard. While often overshadowed by its more active neighbors like Mount St Helens, recent surges in earthquake activity beneath Mount Baker have drawn attention from scientists and residents alike. These seismic events, though subtle, serve as reminders that Mount Baker is an active volcano and could awaken under the right conditions. Mount Baker is one of the tallest and most glaciated peaks in the Cascade Range, rising over 10,700 feet. Unlike Mount St Helens, which erupted explosively in 1980, Mount Baker has not experienced a significant eruption since the mid-19th century. However, its history reveals it as an active volcano, capable of generating lava flows, ashfall, and devastating lahars or volcanic mud flows that could threaten surrounding communities. The recent increase in earthquake activity has reminded scientists and the public that even a quiet volcano like Mount Baker remains dynamic and must be monitored carefully. Seismic surges, or earthquake swarms, occur when clusters of small tremors are detected over a short period. At Mount Baker, these events are typically caused by magma movement, tectonic forces, or changes in the hydrothermal system beneath the volcano. Earthquakes often indicate magma rising or shifting within underground chambers, fracturing rock and creating stress. While not always a precursor to eruption, it signals that Mount Baker's volcanic system is active. Mount Baker's glaciers and snowfields feed an extensive hydrothermal system. Heat from magma beneath the surface can cause water to boil and expand, triggering small seismic events. Mount Baker sits within the influence of the Cascadia subduction zone, where the Juan de Fuca plate is being forced under the North American plate. Stress from this tectonic interaction can generate earthquakes and influence volcanic systems. Recent surges at Mount Baker have been dominated by small earthquakes, typically with magnitudes below 2. While not destructive, these tremors provide valuable clues about the volcano's internal activity. It's always important to look back and revisit what exactly happened for the past decades and centuries with the volcano. In the 40s, Mount Baker experienced a significant eruption, producing ash plumes and lava flows that marked its most recent explosive event. In the 70s, increased fumarole activity caused alarm, though it did not lead to an eruption. This period underscored the volcano's ability to stir without erupting and the importance of close monitoring. The current earthquake surge, while not immediately threatening, echoes these earlier signs of volcanic unrest. If seismic activity escalates, it could signal magma rising closer to the surface, potentially leading to an eruption. Melting glaciers caused by heat from magma could generate destructive mud flows, which could travel through river valleys and impact communities downstream. Even a moderate eruption could release ash clouds that disrupt air travel, contaminate water sources, and damage agriculture. While slower moving than lahars, lava flows could affect surrounding forests and infrastructure. Earthquakes and volcanic activity can destabilize glaciers, leading to avalanches, flooding, or erosion. Changes in gas emissions and hydrothermal activity can also impact nearby ecosystems. Mount Baker is a popular destination for recreation, including skiing, hiking, and mountaineering. Increased volcanic unrest or perceived risks could deter tourism and impact local economies dependent on outdoor activities. The recent earthquake surge has prompted scientists to intensify monitoring efforts at Mount Baker. The USGS and the PNSN use advanced tools to study the volcano's behavior. Just like with the rest of the hazardous volcanoes, networks of seismometers detect small earthquakes, allowing scientists to track magma movement and tectonic shifts. Instruments monitor volcanic gases like sulfur dioxide and carbon dioxide, which can indicate magma rising closer to the surface. Satellites detect ground deformation caused by magma or hydrothermal activity beneath the volcano. Early warning systems and regular updates keep nearby residents informed about potential hazards. While Mount Baker's current earthquake surge does not necessarily mean an eruption is imminent, preparedness is essential for nearby communities. By combining scientific monitoring with community preparedness, the risks associated with volcanic activity at Mount Baker can be effectively managed. The recent earthquake surge at Mount Baker highlights the dynamic nature of this quiet yet active volcano. While these small tremors may not immediately signal an eruption, they serve as critical reminders of the potential hazards posed by Mount Baker. Through scientific monitoring, public awareness, and preparedness, communities can remain vigilant and resilient in the face of volcanic unrest. Mount Baker's rumbling is not a cause for panic, but a call to respect the powerful natural forces shaping the Cascade Range. Mount Adams. Mount Adams, a majestic stratovolcano in Washington state's Cascade Range, has long stood as a quiet giant. While it has not erupted for over 1,000 years, recent earthquake activity beneath the volcano has raised questions about its status and potential hazards. These earthquakes, though small and often unnoticed by the public, are significant in understanding Mount Adams's volcanic system and its connection to the region's larger geological forces. Recent seismic movements beneath Mount Adams have consisted of small magnitude earthquakes, typically measuring less than 2.5 on the Richter scale. These tremors occur at varying depths, often between 3 to 10 kilometers below the surface. While not alarming in isolation, clusters or swarms of small earthquakes can indicate changes deep within the volcanic system. The recent earthquake activity at Mount Adams is significant because it is unusual for a volcano historically considered dormant. Unlike nearby volcanoes like Mount St Helens or Mount Rainier, Mount Adams has experienced far less seismic activity in recent decades, making this surge worthy of scientific attention. Small earthquakes often occur when magma pushes through underground rock, creating fractures and releasing energy. While there is no immediate evidence of magma nearing the surface, its movement in deeper chambers can cause seismic swarms. Mount Adams lies within the influence of the Cascadia subduction zone, where the Juan de Fuca plate subducts beneath the North American plate. Stress in the Earth's crust from this subduction can trigger earthquakes near the volcano. Heat from magma deep below the volcano interacts with groundwater, creating steam and pressure. Shifts in this hydrothermal system can produce small tremors, even in dormant volcanic systems. Mount Adams, though classified as an active volcano, has not erupted in over a millennium. Its last major volcanic activity produced lava flows that spread across the region, creating the rugged volcanic landscapes visible today. Unlike Mount St Helens, which is known for explosive eruptions, Mount Adams eruptions have historically been effusive, producing slow-moving lava flows rather than violent explosions. However, its large size and glacier-covered slopes mean that any future activity, no matter how minor, could still pose significant hazards, particularly in the form of lahars and flooding. Similarly, the recent earthquakes remind scientists and residents that Mount Adams, while quiet, is not extinct, but part of the dynamic Cascade volcanic arc. Even small earthquakes can signal changes in a volcanic system, requiring scientists to intensify monitoring efforts. While there is no evidence of an imminent eruption, increased activity suggests that the volcano is not entirely dormant. Mount Adams' large glaciers mean that any volcanic activity, including heat from rising magma, could trigger glacier melt and lahars. Nearby communities, such as Trout Lake and those along the Klickitat River, could be vulnerable to flooding. The earthquakes also reflect the broader stress of the Cascadia subduction zone. Understanding these tremors helps scientists assess the region's seismic risks, which extend beyond Mount Adams to include potential major earthquakes in the Pacific Northwest. PNSN uses a network of seismometers to detect and analyze earthquake activity in the region. Even the smallest tremors provide valuable data about magma movement and tectonic stress. Satellite-based GPS systems monitor the ground for swelling or deformation, which can indicate rising magma. Instruments measure volcanic gases like sulfur dioxide and carbon dioxide. An increase in gas emissions could signal magma approaching the surface. Scientists analyze heat flow and water systems on Mount Adams to detect changes in its hydrothermal activity. The recent earthquakes beneath Mount Adams remind us that this quiet giant remains a part of the dynamic volcanic landscape of the Cascade Range. While the tremors are small and do not indicate an imminent eruption, they provide valuable insights into the processes occurring deep within the volcano. Scientists are closely monitoring Mount Adams to better understand its activity and prepare for any future changes. For nearby communities, the earthquakes highlight the importance of awareness, preparedness, and respect for the natural forces that continue to shape the Pacific Northwest. Mount Adams stands as both a symbol of beauty and a reminder of the region's volcanic power, urging us to remain vigilant as we coexist with the ever-changing Earth. Mount Hood. Mount Hood, Oregon's tallest peak and a prominent feature of the Cascade Range, has recently experienced increased seismic activity, drawing the attention of scientists, local communities, and environmentalists. As an active stratovolcano, Mount Hood has a history of eruptions, but it has remained relatively quiet for over 200 years. The recent earthquakes, though small in magnitude, provide critical insights into the dynamic processes occurring beneath the surface. Mount Hood's recent seismic activity primarily consists of earthquake swarms, clusters of small, shallow tremors occurring over days or weeks. These earthquakes typically measure between 1.0 and 2.5 in magnitude and occur at depths of 3 to 7 kilometers beneath the surface. While small and often imperceptible to humans, such seismic swarms are significant because they signal changes within the volcanic system. Earthquake swarms are not unusual at Mount Hood, but the recent increase in frequency and clustering suggests that the volcano is experiencing a period of unrest. Monitoring these patterns allows scientists to evaluate the likelihood of volcanic activity in the near future. Small earthquakes often occur when magma moves within underground chambers. The rising pressure from magma causes rocks to fracture, releasing energy in the form of tremors. Heat from Mount Hood's magma system interacts with groundwater, creating steam and expanding fluids that can cause seismic swarms. This activity also contributes to the fumaroles near the summit. Mount Hood lies within the Cascadia subduction zone, where the Juan de Fuca plate is being pushed under the North American plate. This tectonic pressure can trigger earthquakes, even in regions with little direct volcanic activity. Mount Hood's last major eruptive period occurred between 1780 and 1801, producing lava domes and pyroclastic flows. Unlike explosive eruptions such as Mount St Helens in 1980, Mount Hood's eruptions have historically been effusive, with slower lava flows rather than violent explosions. However, the volcano's large glaciers, some of the most extensive in the Cascades, present unique hazards. Even minor volcanic activity could cause rapid melting of glacial ice, resulting in lahars. These fast-moving flows could travel down river valleys, posing a significant threat to towns like Government Camp, Hood River, and other communities along the Columbia River. While most earthquake swarms do not lead to eruptions, they indicate that the volcano remains active. Continued seismic activity could signal magma rising closer to the surface, increasing the likelihood of an eruption. Mount Hood's glaciers make it particularly susceptible to lahars. Even without an eruption, seismic activity could destabilize ice and trigger floods or debris flows, impacting downstream communities. Ashfall, while less likely given Mount Hood's historical behavior, could disrupt air travel, contaminate water supplies, and affect agriculture in the region. To track Mount Hood's seismic activity and assess its volcanic risk, USGS and PNSN employ advanced monitoring technologies. Seismometers detect and locate small earthquakes, providing data on their frequency, depth, and magnitude. GPS and satellite imagery measure any swelling or deformation of the volcano, which could indicate magma movement. Sensors monitor volcanic gases, such as sulfur dioxide and carbon dioxide, which increase when magma rises closer to the surface. Instruments track temperature changes on Mount Hood's surface, particularly near fumaroles and glaciers. The recent seismic activity serves as a reminder that Mount Hood, though quiet for centuries, is still an active volcano. Local communities, emergency management agencies, and residents must prioritize preparedness to mitigate potential risks. Educating residents about volcanic hazards, such as lahars and floods, and providing guidance on how to respond to warnings. Developing and practicing evacuation routes for communities located in river valleys vulnerable to lahars. Ensuring households have supplies to handle disruptions caused by seismic or volcanic activity, such as ashfall or infrastructure damage. Continued investments in monitoring technology and communication systems ensure that residents receive timely alerts. Mount Hood's recent seismic activity underscores the importance of respecting the dynamic nature of this iconic volcano. While the small tremors do not necessarily signal an impending eruption, they highlight the need for continued scientific monitoring and community preparedness. By studying the causes and patterns of these earthquakes, scientists can better understand Mount Hood's volcanic behavior and provide early warnings if activity escalates. Mount Hood stands as both a beautiful natural landmark and a reminder of the region's geological power. With vigilance, collaboration, and proactive planning, communities near Mount Hood can minimize risks and coexist safely with this sleeping giant. The Cascade Range is one of the most dangerous geological regions in North America due to its active volcanoes, the threat of large earthquakes from the Cascadia subduction zone, and the unique hazards of lahars, ashfall, and glacier melt. Its proximity to major population centers further heightens the risk. However, through scientific monitoring, early warning systems, and public preparedness, the dangers of the Cascade Range can be managed. This magnificent yet volatile region serves as a reminder of the power of nature and humanity's responsibility to coexist with and respect its dynamic forces. That's the end of the video. Share your thoughts about the active volcanoes. Have you visited any of them? See you in the next great story.